Let's look now at an introduction to modeling. Now, modeling is one of the more useful applications of math outside of a math class because what it does is it allows you to describe the relationship between different quantities, between different measurements in real life as an equation, or sometimes sets of equations that we can then manipulate. Basically, they distill down something complicated into something much simpler, like a mathematical equation rather than a physical object or a set of objects, and then those equations can be manipulated and used to predict or to describe the situation. Now, there are lots of different kinds of models, but the ones that we're going to be looking at in this in this video are the three of the most common ones that we'll see. That's the linear model, the quadratic model, and the exponential model. When you have quantities, you can measure how one changes with respect to another. So for example, you can measure how someone's height changes with respect to their age. Or you can measure the value of a classic car based off of how old it is, right? Based off of its age. So whenever you have multiple quantities that you're trying to compare, you can always compare them using a graph. So here we could say, okay, we have one variable, which we'll call x, the age of something, the value of an object, the height of a person, or whatever. You have a measurement that you can make. And here's another measurement. The age of a person, the weight of a person, the age of a car, or anything else that you might be measuring. All right? So now, depending on what you're measuring, you can always find sets of ordered pairs. You can always find points that represent those pieces of information. Depending on how those pieces of information line up, you'll either end up with a linear, a quadratic, or an exponential model. So first of all, let's see what the patterns look like. First of all, the patterns don't have to be perfect. They're simply a trend. So for example, here, I have a collection of points. Now, I'm not going to describe what these points are just yet. We're going to go ahead and look at some examples here in a moment. Right now, we just want to see the pattern divorced of any context or of any equations, just the pattern. Let's say here is our collection of points. Okay. Now, this is sort of scattered out, but you notice that all the points, as you move through the graph, follow this path right here, and that path happens to be a straight line. So because the path that these points follow is a straight line, now notice not all of them are going to touch the line. Some of them do, some of them don't. But the general trend is along this line. This would be called a linear model. Whenever you have a linear model, that situation can be summarized, can be modeled, is the phrase that we use, using a linear equation, which you'll often write as y equals mx plus b. A quadratic model is going to have a different pattern. If you plot points and they form a straight line, or approximately a straight line, you have a linear model. However, if your graph bends in a U-shape, something like this, where either it's U-shape facing up this way, or it could be upside down, it could be facing down in the opposite direction, you'll notice that these points do not follow the path of a straight line. They sort of bend and come back the way from which they came. Notice here if I connect my dots, well, it's a very complicated shape, right? But if I simply follow the trend, the pattern that they establish, you notice that these all cluster around this U shape, this bowl shape. Whenever you have a set of points that cluster around a shape like this, then we can use a quadratic model to describe the pattern. When we talk about the model, we mean the equation. So the model is the equation. What the model does, what the equation does, is it gives us a line that describes the path of our points. Right? Here, the path that our points take is a parabola, so we're using a quadratic model, meaning a quadratic equation. Quadratic equations are of the form y equals ax squared plus bx plus c. Okay? And the third kind of model that we want to look at, there's only three models that we're going to look at, although there are many others that exist. These three happen to occur very often in many different fields: biology, chemistry, physics, economics, psychology, sociology. Lots of things appear along one of these three patterns. If the pattern that you have starts off very flatly, but then picks up and goes up very quickly all of a sudden, or the other way around, if it is coming up very quickly and then all of a sudden it just sort of flattens out, that's called an exponential model. So you're going to have one portion of your graph which is very close to being flat. It might go up just a little bit, but almost imperceptibly. It's going to be very flat. And then once you get past a certain point, it'll start to go up very, very quickly, or it can go down very, very quickly. Either one of those is acceptable. This is an exponential model. The pattern being very flat on one side and then going up like that. You can also have one which goes very flatly and then goes down, or you can have one which goes down very quickly and then flattens out. So anything like that, where one edge is flat and the other edge is going up or down very, very quickly, this will be an exponential model. Once again, the model is the equation itself. So this is the model over here. Y equals some number raised to a power. Like that. Now here we see an example of the height progression of a 5-year-old child. So at their 5th birthday, they were measured to be at a height of 109 centimeters. Okay. Now every month they're measured again. So 1 month after their 5th birthday, they have a height of 110 centimeters. A month after that, still 110 centimeters. There's been no appreciable growth. Another month after that, they're at 111. A month after that, 112, and so forth and so on. You notice that their height is progressively climbing this way. Now, notice that it's not following a perfectly straight line. It does sometimes flatten out a bit, and other times it shoots up all at once. This is not a problem when it comes to modeling. When we're modeling something, we're not modeling with the assumption that everything is going to be perfect. Reality rarely is perfect. Reality is rarely going to follow a perfect model, and even if it does, measurements are flawed. The person measuring this might have rounded to the nearest centimeter. They might have had a ruler or a measuring stick that was slightly off. It may have been a very warm day and the metal ruler expanded a bit and made the measurement a little higher or a little smaller than it otherwise would have been. So measurements are generally not considered to be perfect, nor do they need to be. Notice that even though these sort of wander around a bit, they wiggle and wave a bit here, overall, they follow a straight line. And so this would be considered to be a linear model. This situation would be modeled by a linear equation of the form y equals mx plus b. In this case, you could even find what that equation is by picking two of the points that happen to be on the line. Notice right here we have 1 point. At 3 months, they measure 111 centimeters, so 3, 111. And at 8 months, they measure 114 centimeters, so 7, 114. Once you have a few points that are on this line, you can, of course, create the equation to this line of the form y equals mx plus b, and then that equation can be used to model the situation. If you expected the child to continue to grow in this fashion for the next year, you could use this to estimate how tall they would be a year from now, or half a year from now, or whatever amount of time you wish to model. Note that in this section, we're not really concerned with creating the equations. We're simply concerned with describing them, what the properties are, what they look like, and the type of equation that would model them. And for this particular model, you would have something that looks like y equals mx plus b. The next model we want to look at is something that's quadratic in form. An example of this is often seen in physics. Whenever you measure the trajectory of an object, whenever you measure when something is thrown, oftentimes you have a shape similar to this which appears. For example, let's say we measure the height of a toy rocket, something that you fill up with baking soda and vinegar and launch it. It's a small plastic toy that is used to teach children about rockets and about how propulsion works. Right? So note here that it's not going to fly for very long. Again, it's a toy. It's going to go up and come back down in about 6 seconds worth of time. What we do, though, is from the moment of launch until the moment it hits the ground again, we're going to measure how high up it is. So after 1 second of after the launch, it's just under 25 meters, so 24 and a half maybe, somewhere in there. After 2 seconds, it's gone up to, that looks about 37, maybe 38, somewhere in there. After 3 seconds, you have a height of 44 meters. Then, after 4 seconds, it's starting to come back down at 37 meters. And then, right here, after 5 seconds, you're back down to about 24 meters. And then finally, after 6 seconds, you've hit the ground. Notice the pattern. It goes up and then comes back down. Now note, that is the opposite of what we see here. The direction has been flipped, and that's okay. A quadratic model maintains this shape. It doesn't necessarily maintain this position or orientation. So a quadratic model could be higher up. It could be a bowl shape, a U shape up here. It could be down below the x-axis, or as you see in this illustration, as you see in this example, it can be upside down, just like this, where we have it starting from the bottom, going up, and then coming back down. One thing of note when we look at quadratic models is that every quadratic model, when you graph it out, will have one point where the graph turns around. Either because your graph went down, hit that point, and then came back up, or, as we see in our other example, because it went up, got to the top, and then came back down. All right? This point right here is called the vertex of the parabola. Wherever your graph reaches an extreme value, either the maximum or the minimum, and turns around, that's called the vertex. And, as mentioned just a moment ago, it represents the extreme value of this model. It's either the smallest possible value that situation can take, or the largest possible value that situation can take. So in this example, you note that your height will reach a maximum value of 44 meters. These models are especially useful when looking for extreme values. Whenever you say, I have a situation and I want to figure out what is the biggest possible thing something can occur. What is the biggest possible way something can happen? So I have the height of an object. What's the maximum height it will ever reach? I have a business model and I'm trying to figure out what's the maximum profit I will ever achieve. I have a physical situation and I'm trying to figure out what is the minimum amount of energy that it takes to perform an action. Whenever I'm looking for a maximum or a minimum, that's represented by the vertex. So here, the vertex, it represents a max or min value. Finally, our last example is the exponential model. Note again that the exponential model can take two different directions. So even though both of these are exponential models, there is a slight difference in the naming of the two. If ever you have an exponential model which starts flat and then as you move to the right it goes up, this is called exponential growth, for the reason that the graph is growing, it's getting bigger, it's getting taller. However, if you start with something that's very big and start to have it come down and eventually it starts to flatten out so that your graph gets very, very flat toward the right, then here your graph started high and it broke down and it shrunk down until you got a very small, almost zero value. This is called exponential decay. And they're both exponential models. They follow a lot of the same properties, they follow a lot of the same rules, and they even have the same equations. The difference being that one goes up, whereas the other one starts high and gets down low. Whenever you have an exponential model, one thing to note is that it will reach a plateau. It'll reach a flat line. That line represents a lower bound, meaning the graph will never go below that line. Now, in both of these illustrations, you notice that that lower bound is the x-axis. It doesn't have to be. Depending on the situation, it can be something else. But it will always have some bound. So here, this is a bound. And a bound just means this is a line which your graph can't ever cross. So here, this is called a lower bound because it's a graph, because it's a line that your graph can't go below. It's the bottom. There is such a thing as an upper bound, but we're not going to look at that right now. Right here, so this is a bound on your model, on your value, and it means that it represents, a lot like the vertex, it's a maximum or a minimum value. The difference is that in a quadratic model, you actually reach the minimum value. There's actually a point where you hit that on the graph. Whereas in the exponential model, you get very close to the bound, but you never quite reach it. So here, you represent a max or min value that you can reach. Eventually, you'll be at that point. Over here, the bound, this represents, and I'll go ahead and say a lower bound, because that's what this is. It's a lower bound, a bound on the bottom, represents a minimum value that you approach, you get very close to it, but do not reach. So let's take a look at an example of an exponential model. This one comes straight out of economics, and it is the value of a deposit after a certain amount of time based off of compound interest. So here, you're going to deposit $1,000, and I realize I misspelled deposit. Oh well. I have the value of a $1,000 deposit. So I'm going to put $1,000 in a bank, and I'm going to get paid 5% interest. Now, that interest will be compounded monthly. So every month, I accrue more interest. Now, it's not the full 5% every month. 5% is per year, so it adds up to 5%. Right? It's a little bit each month until I get to 5% at the end of the year. Okay, so if I start off with $1,000 and I'm getting paid 5% distributed throughout the year, compounded monthly, after a certain number of years, let's see how much money I have in the account. Okay, well, if I start off with $1,000, well, that's where I started, right? That's my starting value. And then after 1 year, I've gone up just a little tiny bit. It's gone up such a small amount, it's hard to even tell this has gone up, right? If I was at $1,000, maybe I'm now at $1,012, something just slightly higher. And the next year it goes up a little bit more. And notice that at first, the amount that it goes up isn't very much. After 10 years, remember this X represents the number of years. After 10 years, I've gone from $1,000 to, well, I still haven't quite reached 2,000. Maybe I'm at 1,700, 1,800, something like that. It's basically no change at all, right? After 10 years, nothing's happened. It's very, very flat. Notice that after 15 years, I've reached $2,000. Okay, that's not bad. It took 15 years, but I did manage to double the value of my account. Notice that if I keep going, it's going to continue to increase. But as time goes on, it increases faster and faster. The reason for that is because here, I only have $1,000. So if I'm being paid interest, I'm being paid interest on $1,000, which isn't a lot of interest. Over here, I'm being paid interest on $2,000, because that's how much my account is worth. Well, the interest on $2,000 is a little bit more. So my account will grow a little faster. Oh, but then eventually, I reach here, and that is an account worth $4,000. And the amount of interest on $4,000 is a little bit more. In fact, it's a lot more. So it's going to grow even faster. Notice, from 1,000 to 2,000, it took 15 years. From 2,000 to 3,000, it took maybe only 10 years. From 3,000 to 4,000, it took only about 6 years. And as you go forward, you realize that the amount that you have in your account is going to start to grow very, very quickly. And again, the reason for that is when you have very little money in the account, the amount of interest that gets added to it is also very little. But as that interest gets added, you have more in the account, which means you get more interest, and it gets bigger and bigger as time goes on. So once you have $10,000 in your account, well, then the interest on $10,000 is kind of a lot. Notice that's going to go up from 10,000 to maybe 10,500 in just 1 year, just one little step here. So as you keep going, if we were to let this keep going, I only did up to the first 50 years after the deposit. But if you let it keep going for 60, 70, 80 years, this will get very, very big, very, very fast, even faster. So this is an example of an exponential model. Notice that it's growing, hence the name exponential growth. And note that we do have one side that's flat, whereas the other side is going up. Every exponential graph will have that. Every exponential model will have that. Although, as mentioned before, sometimes it'll be on one side versus on the other. If it starts off very low and grows, the way our example just did, then that's an example of exponential growth. On the other hand, if you're starting up very high and then it comes down, that's a model. That's a similar model with a slightly different name. Again, exponential decay. And that's about it. This is simply meant as an introduction to modeling. We merely wanted to see what our basic models look like. Look at an example of what situation would result in one of each of these kinds of models. Note that with this introduction, we don't really talk about how to find these equations. Here, with the model for our amount in our bank account, we have an exponential model, but we don't really talk about what that equation is. Likewise, for the model which shows the height of our rocket after a certain amount of time, we note that this is a quadratic model, but we don't quite mention what that model is. We don't say what the equation is. Y equals to what exactly? And for the height progression of our child, again, we have a linear model, an equation that models this situation as a straight line, but we don't mention how to find that line exactly. Nor are we going to. Finding these lines requires a bit more material than we're going to go into right now. Anyone who takes a business math class, a statistics class, a class in application of math will see more of what is required to make a model, whether it be linear, whether it be quadratic, or whether it be exponential. You'll have to talk about regression models, whether they be linear regression models or any other ones. And you'll have to talk about how to solve a system of equations to actually give an equation based off of some points. Right now, the only one that you probably have some experience in is creating equations of lines for the height progression of a child situation here, where you simply find the slope between 2 points and then use that slope along with one of the points used to find the equation of that line. But for now, it's sufficient if we recognize the patterns, the shapes right here. We recognize the names that are associated to those patterns, to those shapes, and the basic equations, even if we don't have any specific numbers, that are associated to these models. Namely, if you have a pattern that looks like this, it's called a linear model, and it's represented by an equation that looks like y equals mx plus b. If you have a situation with a pattern that looks like this, that's called a quadratic model, and it's represented by this equation, y equals ax squared plus bx plus c. And if you have either of these situations, whether it be growth or decay, those are going to be given by an exponential model, an equation that looks of the fashion y equals a to the x. So that is it for now. If anybody has any questions, comments, or problems, please make a note of those and reach out. And I hope everyone has a nice day.